In the previous class, we provided a qualitative definition for the rate distortion function as the lowest rate at which the output of a source can be encoded while keeping the distortion less than or equal to some specified distortion level. We also investigated the rate and distortion for two different lossy compression schemes. In example 1, we found that the rate was equal to the entropy of the reconstruction alphabet. However, this was the result of the fact that the conditional probabilities for that particular source encoder took on only two values, 0 and 1. Now, this need not be the case always. Let us take another example to illustrate this concept in a better way. So, we consider example 3, which is the same as example 1, where the source output consists of 4-bit words. The source encoder drops the least significant bit of this 4-bit word to generate 3-bit word, and the source decoder multiplies the output from the source encoder by 2 to generate the reconstruction alphabet given here. So, for this example, the source and the reconstruction alphabet is the same as it was in example 1. Now, we use the distortion measure based on the squared error difference, and we also assume that the distortion level is given to be d equal to 225. The problem is to design a lossy compression scheme that satisfies the distortion constraint. So, one such compression scheme that satisfies the distortion constraint would be to randomly map the input to any of the output. That is, conditional probability of yj given xi is equal to 1 by 8 for I equal to 0, 1, 2 up to 15 and j equal to 0, 2 up to 14. We can see that this conditional probability assignment satisfies the distortion constraint. As each of the 8 reconstruction value is equally likely, we get the entropy for the reconstruction alphabet, that is hy is equal to 3 bits. However, for such a lossy compression scheme, we are not transmitting any information. So, we could exactly get the same results by transmitting 0 bits and randomly picking y at the receiver. What this example illustrates is that the entropy of the reconstruction, that is hy, cannot be a measure of the rate. Now, let us look at the average mutual information, that is I x y, which is given by H x minus conditional entropy of x given y, or this can be also rewritten as entropy of y minus conditional entropy of y given x. Now, this can be rewritten as double summation over I j probability of x I, conditional probability of y j given x I log of conditional probability y j given x I over probability of y j, where probability of y j is equal to summation over I of conditional probability y j given x I multiplied by probability of x I summed over I. So, this mutual information is a measure of correlation between the random variable x and y. Now, in the rate distortion theory, the source, that is P x I, is given, so that average mutual information will be regarded as a function of the conditional probabilities y j given x I. So, we can write the average mutual information as a function of conditional probabilities. Now, Shannon in his 1959 paper on source coding has found the relationship between the minimum rate and the distortion, and this is stated as follows. So, the rate distortion function is equal to minimum of average mutual information, and this minimum is over the conditional probabilities, where this conditional probability belongs to the set given by all those conditional probabilities which satisfies the distortion criterion. The paper by Shannon is stated here. Coding theorems for a discrete source with a fidelity criterion. It had appeared in IRE International Convention Records volume 7 part 4 in 1959. Now, we will not go into the proof of this relationship. However, we can at least convince ourselves that defining the rate as an average mutual information gives sensible answers when used for the example discussed. So, if we consider example 1, which we had discussed in the previous class, we calculated the average mutual information to be 3 bits, which is what we set the rate was. In fact, notice that whenever the conditional probabilities are constrained to be of the form given equal to 1 for some j equal to j I is equal to 0, otherwise then conditional entropy H of y given x is equal to 0, and in this case mutual information is equal to entropy of y, which had been a measure of rate. In example 3, the average mutual information is 0 bits, which accords with our intuitive feeling of what the rate should be. Again, whenever conditional entropy H of y given x is equal to H of y, that is, the knowledge of the source gives us no knowledge of the reconstruction, then mutual information is equal to 0, which seems entirely reasonable. We should not have to transmit any bits when we are not sending any information. At least for the examples discussed here, it seems that the average mutual information represents the rate. However, based on our earlier study, we can say that the average mutual information between the source output and the reconstruction is a measure of the information conveyed by the reconstruction about the source. So, the natural question is, why are we then looking for compression schemes that minimize this value? Now, to understand this, we have to remember that the process of finding the performance of the optimum compression scheme had two parts. In the first part, we specified the desired distortion. So, the entire set of conditional probabilities over which the average mutual information is minimized satisfies the distortion constraint. Therefore, we can leave the question of distortion or fidelity aside and concentrate on minimizing the rate. So, this provides some kind of qualitative justification for the rate distortion formula. Finally, how do we find the rate distortion function? There are two ways to compute the rate distortion function. One approach is basically a computational approach. The algorithm is relatively simple. We will have a look at this algorithm little later, and the other approach is based on finding a lower bound for the average mutual information and then show that we can achieve this bound. We will use this approach to find the rate distortion functions for two important sources. So, the first important source is a binary source for which we will calculate the rate distortion function as follows. Suppose we have a source alphabet consisting of 0, 1 with probability of 0 equal to small p, and let us assume that the reconstruction alphabet is also binary. We assume that the distortion measure is based on Hamming distance, that is d of x I y j is equal to x I modulo 2 addition or exclusive OR operation between x I and y j. Given this, let us find the rate distortion function for this source. The solution to this problem follows. Assume without loss of generality that p is less than half. So, for d, that is the specified distortion level greater than p, an encoding scheme that would satisfy the distortion criterion would be not to transmit anything and fix y equal to 1. So, for d greater than or equal to p, we can say R d is equal to 0. Now, we will find the rate distortion function for the distortion range between 0 and less than p. In order to do this, let us first find the lower bound for the average mutual information. Average mutual information is equal to entropy of the source minus conditional entropy of the source given reconstruction. This can be rewritten as entropy of the source minus conditional entropy of x XOR y given y. Now, we have used the fact in writing this step that if we know y, then knowing x, we can obtain x XOR y and vice versa, as x XOR y XOR y is equal to x. Now, this can be written as entropy of x minus entropy of x XOR y. From here to here, we use the relationship that the conditional entropy is always less than the entropy. from this step to this step, we use the fact that conditioning always reduce the entropy, that is because h of x given y is always less than equal to h of x. Now, h of x is equal to minus p log to the base 2 p minus 1 minus p log to the base 2 of 1 minus p, and it is indicated as h b p. This is a binary entropy function which we had seen earlier, and it is plotted as shown here. Note that h b p is equal to h b 1 minus p. So, given that h x is completely specified by the source probabilities, our task is now to find the conditional probabilities such that entropy of x XOR y is maximized while the average distortion is less than the specified distortion level. Now, entropy h x XOR y is simply the binary entropy function h b probability of x XOR y is equal to 1, where probability of x XOR y equal to 1 is equal to joint probability of x is equal to 0, y is equal to 1 plus joint probability of x is equal to 1, y is equal to 0. Therefore, to maximize this quantity, we would like probability of x XOR y equal to 1 to be as close as possible to 1/2. Based on this plot. However, the selection of probability of x XOR y has to also satisfy the distortion criterion. The distortion is given by zero multiplied by probability of x is equal to 0, y is equal to 0 plus 1 into probability of x is equal to 0, y is equal to 1 plus 1 into probability of x is equal to 1, y is equal to 0 plus 0 multiplied by probability of x is equal to 1, y is equal to 1, and this can be written as probability of x is equal to 0, y is equal to 1 plus probability of x is equal to 1, y is equal to 0, which can be rewritten as probability of y equal to 1 given x is equal to 0 multiplied by probability of x is equal to 0 plus probability of y equal to 0 given x is equal to 1 multiplied by probability of x is equal to 1, that is 1 minus p. But this is simply the probability that x XOR y is equal to 1. Therefore, the maximum value that probability of x XOR y equal to 1 can have is d, because average distortion is less than or equal to d. Now, our assumptions were that d is less than p and p is less than or equal to half, which means that d is less than half. Therefore, probability of x XOR y equal to 1 is closest to half, while being less than or equal to d when x XOR y is equal to 1 is equal to d. Therefore, we get mutual information greater than or equal to binary function h b p minus the binary function h b d. Now, we will show that this lower bound is actually the rate distortion function and can be achieved by finding a joint distribution or conditional probability distribution for the given source distribution that meets the distortion criterion and has mutual information equal to the rate distortion function. Now, for specified distortion level between 0 and p, we can achieve the minimum value of average mutual information in this relationship by choosing x y to have the joint distribution given by the binary symmetric channel as shown here. Let us assume that the probability of y equal to 0 is equal to r and probability of y equal to 1 is equal to 1 minus r. So, we choose the distribution of y at the input of this channel, so that the output distribution of x is the specified distribution, that is p and 1 minus p. So, if we assume r to be the probability of y equal to 0, then choosing r as follows. So, we get the value of r given by this expression. Now, if d is less than or equal to p, and which is less than or equal to half, then probability of y equal to 0 is greater than or equal to 0, and probability of y is equal to 1 is also greater than or equal to 0, and we then have mutual information equal to h b p minus h b d. Therefore, for d less than p and p less than or equal to half, the rate distortion function is equal to binary entropy function h b p minus the binary entropy function h b d. Finally, if p is greater than half, then we simply switch the roles of p and 1 minus p. So, putting all this together, the rate distortion function for a binary source is binary entropy function as function of p and binary entropy function as a function of a specified distortion level d for is equal to 0 for d greater than minimum of p 1 minus p. Now, this function is illustrated in the figure. So, it is monotonically decreasing function. For p equal to 0.5, the maximum value of distortion for 0 rate is equal to 0.5, and maximum value of the rate for 0 distortion is given by the entropy of the source for p equal to 0.5, which is equal to 1. For p equal to 0.2, the maximum value of the distortion is 0.2 for the rate equal to 0, and for distortion equal to 0, the maximum value of the rate is given by the entropy of the source for p equal to 0.2. So, having calculated the rate distortion function for a binary source, let us proceed to calculate the rate distortion function for another important source, that is a Gaussian source. Again we will follow the same approach. We will write down the average mutual information for a Gaussian source and show that the lower bound for that average mutual information is achievable. So, we have a continuous amplitude source that has a 0 mean and Gaussian PDF with variance equal to sigma squared. So, we have a normal distribution, that is Gaussian distribution with 0 mean and variance equal to sigma squared. We assume that our distortion measure is again the squared error measure. So, our distortion constraint is given by average squared error less than equal to some specified distortion level d. So, first we will calculate the rate distortion function for specified distortion level less than sigma squared. Mutual information is equal to differential entropy minus conditional entropy of x given y. This is equal to differential entropy minus conditional entropy of x minus y given y, which is greater than or equal to h of x minus h of x minus y. From second step to third step, the reason is conditioning always reduces entropy. So, in order to minimize the right hand side of this equation, we have to maximize the second term subject to the constraint given by mean squared error to be less than some specified distortion level t. Now, the second term is maximized if x minus y is Gaussian based on our earlier study, and the constraint can be satisfied if expectation of x minus y squared is equal to t. Therefore, h of x minus y is the differential entropy of a Gaussian random variable with variance d, and the lower bound becomes I of x semicolon y greater than or equal to half log 2 pi e sigma squared minus half log 2 pi e d. This is equal to half log sigma squared by d. Now, this average mutual information can be achieved if y is 0 mean Gaussian with variance sigma squared minus d, and conditional PDF is given as follows. Now, for d greater than sigma squared, if we set y equal to 0, then mutual information between x and y is equal to 0, and the mean square error is equal to sigma squared, which is less than d. Therefore, to summarize, we can say that the rate distortion function for the Gaussian source can be written as half log sigma squared by d for d less than or equal to sigma squared, and it is equal to 0 for d greater than sigma squared. This relationship is illustrated in figure. Again, we see that the rate distortion function is monotonically decreasing function with increasing d. Now, we can find out the maximum allowable distortion, that is d max, as follows. If no information is transmitted, the best choice which the receiver can make consists of choosing the average value, which in this case is equal to 0, because this has the largest probability density and is therefore the most probable transmitted value. The error which is now made is x minus 0 squared is equal to x squared, and the average error is equal to expectation of x squared, which is equal to sigma squared. From this, it then follows that d max, which is the minimum distortion for R d equal to 0, is equal to sigma squared. We further see that R 0 increases to infinity if d is made smaller and smaller. This is of course a mathematical abstraction. In practical systems, d will be bounded by the smallest measurable signal value. So, in conclusion, we can say that like the differential entropy for the Gaussian source, the rate distortion function for the Gaussian source also has the distinction of being larger than the rate distortion function for any other source with a continuous distribution and the same variance. Now, this result is especially very valuable because for many sources it is very difficult to calculate the rate distortion function. In this situation, it is helpful to have the upper bound on the rate distortion function. Now, it would be also nice to have a lower bound on the rate distortion function for a continuous random variable. We will investigate this case in the next class, and we will also look at the computation approach to calculate the rate distortion function.